So good evening, good afternoon, everyone, and welcome to this lecture. This is lecture number 10, and we were dealing with magnetic force on a wire, and we had seen different cases of what happens when we have two wires, and we had seen that when two wires carry current in the same direction, they will always attract each other. Do we remember this, or have we forgotten this? We remember this? And if they are having current in the opposite direction, they will repel each other. The force per unit length between two parallel wires separated by a distance of 1 meter when 1 ampere of current flows through them is 2 pi into 10 raised to the power minus 7 Newton per meter, and that is the definition of 1 ampere. Do we remember this definition of 1 ampere?
Yes, sir.
Okay. Now, what we're going to do next is something known as the magnetic moment of a current carrying wire. So that will be the next heading. Shall I do this or shall I do this? Okay, let us do. Before going on to do this one, let us just go back and see one more thing at this point in time, since we are dealing with force, and after that we might not be coming back to this topic. um let me give you this small recap of what we had done. We had seen the magnetic field due to a small current carrying element of the wire, and we had seen the Biot-Savart law, and we had derived the magnetic force or magnetic field due to a wire. Now I don't know, I don't think that we had seen the magnetic field in different forms. So let us write these forms before going ahead. Magnetic field in various forms. What we had seen was the magnetic field created by a segment of the wire, the current carrying element of length dl, and if you could recollect, this was the magnetic field due to the current carrying element of the wire. Db was mu naught by 4 pi I dl cross r by r cube. Do we remember this formula?
Yes, sir.
And we had seen that the direction of this magnetic field can be found out by the direction of dl cross r. Now the same formula for a current carrying element or a current carrying segment can be written in the form of j vector, and if you remember, this j vector is your current density vector. Do you remember current density vector?
Yes, sir.
The same formula, if it is written in terms of current density vector, and I think not told you this formula. This is the formula when the same formula is written in terms of current density vector. So note this form: mu naught by 4 pi is remaining same. Instead of I dl cross r by r cube, we have j cross r divided by r cube multiplied by dv. What is this dv? This dv is the small volume of which we are trying to find out the magnetic field, and how IDL becomes J into dV. It is explained in the explanation given below. Do we understand this? So these are the two different forms of magnetic field due to a segment of a wire. What is written on the right hand side? The third side is the magnetic field created by a moving charge. Now remember this, the third formula is the actual form of Biot-Savart law when it is given in the form of magnetic field created by a point charge. Magnetic field created by a point charge which is moving with a velocity. For example, if I have a point charge, positive point charge, let us say plus q, moving with a velocity v vector, and I have a point P here whose radius vector is given by r vector. This point charge is going to create a magnetic field, a small magnetic field dB at this point, dB at this point P, and the value of that magnetic field in vector form will be given by this formula, mu naught by 4 pi q v cross r divided by r cube. If this charge is positive, we will use the positive value. If this charge is negative, we will use the negative value. This will become the vector form. This will become the vector form of magnetic field created by this point charge. If you want, you can also write the scalar form. The scalar form will be dB, will be mu naught by 4 pi q v sine theta. Don't know why this happens. Okay, so as I was telling you, you can also write the scalar form of this equation, and the scalar form of this equation looks like this. I will have dB, which will be equal to mu naught by 4 pi q v sine theta divided by r square. That will give you the magnitude of the magnetic field. What is theta here? Theta here would be the angle between v vector and r vector. That will give you the magnitude of magnetic field. How you will get the direction of magnetic field? How will you get the direction of magnetic field? This will give you the magnitude of magnetic field. To get the direction, what do? You do the cross product of v with r vector, and that will give you the direction of magnetic field. If I do the cross product of v with r, v is like this, r is downward, so the magnetic field will be going inside. So this magnetic field at this point will be going inside. Now remember, this right hand product, this cross product will always give you the magnetic field created by a positive charge. There is no way to find out magnetic field created by a negative charge. The only way you can find out the magnetic field due to a negative charge will be you will use the right hand thumb rule and reverse the direction. Do we understand what I said?
Yes, sir.
So note down these formulae. The third form is the most important one. The second form is also important. It will come in JEE Advanced if the question comes in that way. I'll give you 2 minutes to give me the answer, to note it down. Let me know once you are done. Everyone has understood this, what I have said?
Yes, sir.
2 minutes you have. Okay, then we move ahead and we try to solve this question. In this question, we have an electron whose charge is E, negative, because it's a negative charge. It's moving in a circular path of radius r. As you can see, the velocity or the speed of the particle of this electron is given as v. What you have to find out is the magnetic field created at the point O because of this moving charge, and I'll give you 2 minutes to think about this. Try to solve this question in two different ways, and I hope that we can make sense of these two different ways. I'll give you 2 minutes. If you can do it on your own, nothing like it. Let me know once you're done. So you have to find out the magnetic field due to this charge. Which formula should you apply? Which formula are you going to apply? Tell me. No idea? Do you have any idea which formula will I apply?
Centripetal force equals to magnetic force.
Take a deep breath. Open your eyes again. And now again think and tell me which formula should I apply here. Deep breath. Now think again and tell me which formula should I apply here. I have to find out the magnetic field at the center of this. Which formula should I apply here? Yes,
Third formula, sir, in scalar form.
apply it. You get your answer. So, what is the third formula? Magnetic field dB is equal to mu naught by 4 pi q v sine theta divided by r square. You just apply it and you get your answer. So what is the magnetic field dB? Mu naught remains mu naught. 4 pi remains 4 pi. Instead of charge, you get E. Then you get V, the speed. What is the angle between V and R here?
90 degrees.
How much? How much is the angle between V and R here?
90 degrees, sir.
90 degrees divided by radius square. And that is your answer, my dear friend. That
Got
is
it, sir.
the magnetic field created by this electron at the center of the circle. But wait, what is the direction? What is the direction of the magnetic field? Yes? V at this point is upwards. Center is here. What is the direction of magnetic field? V cross R. What is the direction of magnetic field? What is the direction of magnetic field?
SK.
But plus K is the direction of magnetic field produced by a positive charge. This is a negative charge. What is the direction of magnetic field produced by this negative charge? Electron. It would be inside, the
Yes, sir.
opposite of outside. And that is the answer. The direction of magnetic field is inside. Do we understand this? Yes or no?
Understood, sir.
There is one more way in which you could have solved the same question. What is that one more way? This charge is moving in a circle. Charge moving. That means it is a current. It is a circular current carrying wire. What is the magnetic field at the center of a current carrying wire? Circular current carrying wire. What is the magnetic field at the center of a circular current carrying wire? Anyone
Zero,
remembers
sir.
it? Huh?
Zero.
0, sir. Well done, sir. So the answer is 0. So this answer is wrong. Well, it was not 0, beta. You've forgotten everything, and that is not a good time to forget. It was mu naught I by 2R. Magnetic field at the center of the coil. Mu naught I by 2R. The only thing I have to calculate is the value of I. How will I get the value of I? Current. Current is charge Q divided by time period capital T. Charge Q divided by the time period capital T. Charge is E. Time period is 2 pi by omega. So 2 pi into omega. Now if omega is given, you could use omega. Here omega is not given, here V is given. So you can find out the value of omega. What is the relation between V and omega? Yes. What is the relation between V and omega?
V is equal to R omega.
V by R.
V is equal to R omega. So omega is V by R. So I can now write it as E V by 2 pi R. And then I can write the magnetic field. I can just put the value of I in the formula for the second method, and I will end up with the same answer, mu naught EV by 4 pi R squared. This is the answer that I got converting the charge into current and getting the answer. Now, to find out the direction of magnetic field, I can find it out from the charge or I can find it out from current. If negative charge is moving like this, anti-clockwise, what is the direction of current? If negative charge is moving like this, what is the direction of current?
Inside.
If negative charge is moving like this, what is the direction of current? Well, the direction of current is opposite to the motion of electrons. So current is like this. If current is moving clockwise, magnetic field will be going inside. So I could also find out the direction of magnetic field in that way. Whatever way you do, you will end up with the same result. I'll give you 2 minutes to note this down. If you have any doubt, please ask. So we move ahead. On the same lines, we can now write the next heading, and the next heading is force between two charges. Force between two charges. Now, as you could recollect, if there are two charges, stationary charges, Q1 and Q2, separated by a distance of r, what is the force between the two charges? If the two charges are positive charges, you can write down the force, which is the electric force or electrostatic force, that will be equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Yes or no? We understand this? Yes or no? First listen to me, then I'll give you time to write. Do we understand this? Yes or no?
Yes,
That
sir.
is the electrostatic force. Now, if I start moving these charges, and remember that's the very important factor, if both are positive charges, same charges, like charges, and moving in the same direction, V1 and V2, V1 and V2, you can find out the magnetic force between them. How are you going to find out the magnetic force between them? You are going to find out the magnetic field created by the first charge, and you are going to find out the force on the second charge. No matter how you do it, you will end up with this answer. Now remember, if the charges are like and moving in the same direction, they will experience attractive force because of magnetic force. Do we see this? Do we see this pink force, which is a magnetic force? It is attractive in nature. Whereas the green force, whereas the green force, whereas the green force, the green force is like charges. Do we see this? If
Yes, sir.
I find the ratio of these two forces, This is just for your academic interest. If you find out the ratio of these forces, the ratio will be mu naught into epsilon naught multiplied by V square. Now you have to remember that mu naught into epsilon naught is 1 by C square, and therefore you will see the magnetic force and the electric force. The ratio is V by C ka whole square, where V is the speed of the charges and C is the speed of light. And you know that the speed of light is very high, large, and therefore the magnetic force between two moving charges will be very small compared to the electrostatic force. But when you talk about a current carrying wire, the magnetic force, because of there are a large number of charges, the magnetic force might be stronger. Do we understand what we have done here? Yes or no? I'll give you 2 minutes to note this down. And this is the first question on the same point. A vertical wire carrying a current in the upward direction is placed in a horizontal magnetic field directed towards north. The wire will experience a force towards which direction? I'll give you 1 minute to think about it. So how are we supposed to do this? It is pretty simple. If I just show you this diagram, everything would be clear from this diagram. Everything would be clear. Current is going up, magnetic field is here, dl cross b, and that is your force which is going in the westward direction. Do we understand this? Yes or no? No, yes. Okay. This is the next question. This is from a previous year JEE. The time it was known as IITree. Yes? Any doubt? Next question coming up. Question number 2. I'll give you 2 minutes to solve this. Wires 1 and 2 carry current. It's written T1 and T2. It will be I1 and I2. Printing mistake. Inclined at an angle of theta to each other. What is the force on a small element dl of wire 2 at a distance r from wire 1 to the magnetic field of wire 1? Take a deep breath. Think about it. Give me the answer. Same question may come in your exam 5 days from now. How did you get option B? Yes. How did you get option B? How are you supposed to find this? If you remember, we had calculated a formula for magnetic field between two parallel wires separated by a distance of r. Yes or no? And there we had seen the force per unit length. Force per unit length. Force per unit length is mu naught I1 I2 by 2 pi r. Yes or no?
Yes, sir.
That was when the wire were parallel. And if I want to find out the magnetic field on any segment of this wire, let us say of length dl, what will I do is I will just multiply it by the length of the segment dl. Yes or no? Yes
sir.
or no?
Yes, sir.
So basically, I am going to do the same thing. The only thing, the wire is not parallel. So what I am going to do is, this is the dl segment. I am going to take that element of that segment which is parallel to the wire. Right? So this angle is given as theta. So this angle becomes 90 minus theta. Do we understand this?
Yes, sir.
So this segment which is parallel becomes dl sine of 90 minus theta, which is cos theta. Yes or no? Do we understand this? Do we understand this, beta? I have taken that segment, the portion of that segment which is parallel to the wire, and therefore the answer becomes mu naught by 2 pi r I1 I2 dl cos theta. Do we understand this? This is the way you have to do any question which comes in this particular category. Do we get this?
Yes, sir.
Everyone understands this? I'll give you a minute to note it down. Note it down and let me know. Then this is the next question. If I remember correctly, this question has come in one of recent IITs or JEEs. Anyways, this is how questions are framed these days. A conductor PQ RSTU, each of side length L, is bent in the form of this figure. It carries a current I and is placed in a uniform magnetic field B, which is parallel to the positive y-axis. You can see the y-axis is somewhat different here. The force experienced by this wire and its direction is. That should be a simple question, I think. Let me see if you can get me the answer for this one. I'll give you 2 minutes to give me the answer. So how are we supposed to do this? There are different ways. I'll do it by one way. What is the force on this wire, PQ? Pink wire, PQ? Pink wire,
Zero.
PQ? 0. That is correct. What is the force on this wire? TU. Again, I am calling it pink.
0.
The only wire left is this wire. The length of this wire is I. What is the force on this wire? The length of this wire is L. I into B into L into sine 90. Only answer which has IBL is option C. So that is the correct option. You can also find the direction of magnetic force. DL is in this direction. B is in this direction. The force is going to go up. Up means plus Z according to this sign convention. The correct answer is IBL along positive Z axis. I'll give you 2 minutes to note down the answer. Then comes this question, sir, and I want a quick answer from this question. A conductor is in the form of a right angle triangle ABC. The length of the side AB is 3 centimeter. The length of the side BC is 4 centimeter. It carries a current of 10 ampere. There is a uniform magnetic field of 5 Tesla perpendicular to the plane of the conductor. What is the force on this conductor? I'll give you 2 minutes to give me the answer. Option C is correct. How did you get the answer, beta? May I know? How did you get the answer?
IBL, sir.
IBL. So the length is 3 centimeter plus 4 centimeter, 7 centimeter, right?
No, sir.
Then, sir, how?
5, sir.
How 5, sir?
Right angle triangle. Square root of 3 square plus 4 square.
But the third side is not there, sir. So how did you do square? The third side is not there. How did you do it square?
By using Pythagoras theorem.
Why you use Pythagoras theorem? What is
It
the
is
need?
right angle triangle, sir.
So what? The right angle triangle is like this. You have to find out the force on the conductor is like this. It has got a green branch which goes like this, and it has got a pink branch which goes like this. You have to find out the force on this conductor. Why did you use right angle triangle here? Why did you use right angle triangle here? Why did you use right angle triangle here? Why did we use right angle triangle here? Yes? Just because it is given right angle triangle, you find out the third side. What is the use of that? The question is like this. Why did you use right angle triangle? Why did you find out the third side? Tell me. Well, because you have forgotten things. If you close this right angle triangle by this wire, blue wire, it becomes a closed wire, a closed loop of wire in a uniform magnetic field. And if you have a closed wire in a uniform magnetic field, a closed loop of wire in a uniform magnetic field, a closed loop of wire in a uniform magnetic field, a closed loop of wire in a uniform magnetic field, a closed loop of wire in a uniform magnetic field, a closed loop of wire in a uniform magnetic field, a closed loop of wire in a uniform magnetic field, then the force on this entire loop is zero. That means whatever force is acting on the green and the pink wire, equal and opposite force will act on the blue wire. The length of the blue wire is 5 meter. It is easier to find out the force on this wire. I into B into L into sine of 90. That will give you the answer as 2.5 Newton. The magnitude of the force will be same. The direction of force on the other two wires, the sum of the force would be opposite to this wire. And therefore the answer is 2.5 Newton. I'll give you 2 minutes to note down this one. Then comes this question, sir. A wire of length L carries a current I along the x-axis. A magnetic field exists which is given by B is equal to B naught I hat plus J hat plus K hat Tesla. Find the magnitude of magnetic force acting on the wire. I'll give you 2 minutes to give me this answer. Option B, sir, I think is the right option, sir. How did you get the answer? Option B. So the magnetic field is uniform and the wire is straight. So what you got to do? If I want to write the solution, what you got to do? Force vectorly, I can use I L cross B. Yes or no? No, yes. I can use I L cross B. Yes or no? Yes or no? Are we there, beta?
Yes, sir. Yes, sir.
Force in vector form. If I write current is I. Now length can be written as length can be written as L into I hat. Yes or no? Cross magnetic field is B naught into I plus J plus K. Do we understand this, everyone?
Yes, sir.
You just have to take the
Yes, sir.
product. I cross I is 0, I cross J is K, and I cross K is minus J. So what you will have after this is I L into B naught into I think J, no sorry, K minus J. Yes or no?
Yes, sir.
You can now find out the magnitude of this force. One component is along J, the other component is along K. The magnitude will be root 2 times I L B naught. We understand this? Yes or no? So the answer would be option C. Sorry, option B. B naught I L root 2. We all understand this? Yes or no?
Yes, sir.
Everyone has noted this down?
Noting, sir.
Okay, I'll give you a minute. Note it down. And I'll give you this question. This has come in a previous year JEE. Have you noted it down?
Yes, sir.
Yes,
This is
sir.
the next question, and I'll give you 2 minutes to think about this. A conducting loop carrying a current I is placed in a uniform magnetic field pointing into the plane of the paper as shown in the figure. So you have a conducting loop. The figure is not drawn. I'll draw the figure. This is a conducting loop like this. It carries a current I. So let me start again. It got stuck. So I have a conducting loop. Since it is a loop, it could be of any random shape. It carries a current I and it is placed in a uniform magnetic field like this. Then you have 4 options. This is a question from the previous year JEE. Give me the correct answer. I'll give you 2 minutes to think about it. Option B is correct. It will expand. I have already given this question to you in your notes. If you place any random shape loop, it will expand and it will form a circular loop. Do we remember that? And I
Sir.
had also told you what will be the tension in that loop. Can anyone tell me what is the tension in that loop?
BIL by 2 pi.
Well done. Just to refresh your memories, this was what we had discussed before your vacations. An arbitrary loop, BIL by 2 pi, where L is the length of the loop. So don't forget it because this question has come in a previous JEE. So it's very likely that this question could be repeated. I'm again relying on the fact that these type of questions are coming. I'm giving you all types of questions which I think are possible to come. This is the next one. This is a question which you might have seen in a SC Verma. This is the similar question. It has 2 types of question, I think. This is one of those. Where is the question? Let me paste it again. What's happening? Something not properly. Okay. Here I think it comes. A circular loop of wire of radius A carrying current I is placed in a 2-dimensional magnetic field. The center of the loop coincides with the center of the field. The strength of the magnetic field at the periphery of the loop is B. Find the magnetic force on the wire. You can see this type of magnetic field is going actually radially outward. Here the magnetic field is going like this. Here it is like this. Here it is like this. here like this, here this, here this, and here this, and here this. You have to find the force on the loop. I'll give you 2 minutes to give me the answer. Option D is correct. Now remember, this magnetic field at all points on the wire, on the circular loop, is perpendicular. So if I find out the direction of magnetic force on any point, on the top point, DL is like this, B is like this, the magnetic force will come out. For all these points, magnetic force will come out. So all the magnetic force on small wires are getting added up. So it is I into L into B, but this L now becomes 2 pi A because all the forces are coming outside and are getting added up. So the answer is 2 pi A into 2 pi A into I into B. Do we understand this, everyone?
Yes, sir.
Yes or no? No, yes. Well done. This was a bit tricky question. Well done that you could do this. That takes us to the next question in line. And this is the next question, and I'll give you 2 minutes to solve this. You have a wire ABC carrying a current I. These type of questions are coming these days. It is bent in the form as shown in the figure in a uniform magnetic field of magnetic induction B. The length of the side AB is L. Angle ABC is 45. Both the wires are at an angle of 45. What is the force on the wire A B to BC? The length of both the wires is not given. A to B is given as L.
√2.
So how are you supposed to do this? The length of this side will be L, yes or no? And the length of this side will be how much? √2L, yes or no? Yes or no?
Yes, sir.
Then if I talk about the force on this pink wire, the force on this pink wire, I'm only talking about the magnitude. The force on this pink wire, F will be equal to I into L into B into sine of 90. So ILB, yes or no?
Yes, sir.
The force on this green wire, I'm talking about the magnitude only. Let me call this as F2 and let me call this as F1. The force F2 will be equal to how much? I into length is √2L into magnetic field is B into sine of the angle between DL and B. What is the angle between DL and B? Sine of 45, yes or no?
Yes, sir.
You will get cut and you will get the ratio of F1 and F2 as 1. Yes or no? No, yes.
Yes, sir.
The correct option has to be 1. The ratio is 1. Do we get this? Yes or no? No, yes.
Yes, sir.
This question, and I hope I can get a quick answer for this one. These are the type of questions that are coming in the exam these days. And here is the question. A long wire A carries a current of 10 ampere. Long means infinite. Another long wire, infinite, which is parallel to A, separated by a distance of 0.1 meters from A, carries a current of 5 ampere in the opposite direction. What is the magnitude and nature? Nature, you can straight away tell me. Will it be attractive or will it be repulsive?
Sir.
It would be? Okay. Let's wait for the answer then. I'll give you 2 minutes. So, what is the Force between two parallel wires, force per unit length. We have already seen the formula for force per unit length. The force per unit length between two parallel wires is mu naught by 2 pi I1 I2 divided by R, where R is the distance between them. You just have to put the values and you will get the answer. You will get the answer as 10 raised to the power minus 4 Newton per meter. That is the answer that you are going to get. Both the wires carry current in the opposite direction. Opposite direction current, the force is repulsive. So the answer is A. The magnitude is 10 raised to the power minus 4 Newton per meter and the direction is repulsive. When two wires carry current in the same direction, force is attractive. In the opposite direction, force is repulsive. I'll give you a minute to note it down and then we'll move on to the last question for today's class. Then this is the last question for today's class. You have three long straight wires. The force experienced by 10 centimeter length of wire Q. 10 centimeter length of wire Q. I'll give you a minute to give me the answer for this one. So how are we supposed to do this? We have to find the force on the pink wire. The pink wire carry currents in the downward direction. Because of this green wire which is carrying current in the upward direction, will it experience attraction or repulsion?
Repulsion.
Repulsion. So let me call that as the green force F1. Because of this blue wire which is again carrying current in the upward direction, will it experience attraction or repulsion?
Repulsion.
Repulsion. Let me call that force as F2. Let us find out and write the value of F1 and F2. What is the value of F1? Mu naught by 2 pi. I1 is 20 amps multiplied by I2 is 10 amps divided by 2 pi r. Distance is 2 centimeter, 2 in raised to the power minus 2 multiplied by the length of the wire. The length of the wire is 10 centimeter, 10 into 10 raised to the power of minus 2. F2 mu naught by 2 pi multiplied by I1 is 30, I2 is 10, distance is 10 centimeters, length of the wire is also 10 centimeters. So at the end, I multiply it by 10 centimeters, both of which are repulsive. This answer I am given is 2 into 10 raised to the power minus 4. You have to check it. This answer is given as 0.6 into 10 raised to the power of minus 4. Both are in opposite directions, so the net force becomes F1 is more. So the answer would be the green one, F1 will win, and 1.4 into 10 raised to the power minus 4 Newton towards, sorry, it is left towards right. So the correct answer has to be option number A. Do we understand this? Yes or no? No or yes? Well, that's it for today's class. And we will move ahead and see the next portion in tomorrow's class. And hopefully we'll be able to wind up this topic by your 20th, by day after tomorrow. Everyone understood what I've done here? Yes or no?
Yes, sir.
Okay, then I'll see you tomorrow. Take care and God bless you. If you have any doubts, you're free to ask them.